Welcome back, AP Calculus students, to your targeted review. Today's focus is split between two topics, implicit differentiation and related rates. I think they both tie in well to each other because ultimately at some point you're going to be taking the derivative with respect to a variable that might not be the independent variable in the problem. Or there might be multiple variables in the problem and you're going to be taking the derivative with respect to one of them. Okay, so let's rock and roll. We're going to start with beware your derivative with respect to piece on here. And just a friendly reminder, when you do d dx of x, and this isn't perfect, but I'm going to go with it anyways, you could think of this x moving up top, and it's dx over dx, which just becomes 1. So the derivative of x is 1. But when you do d dx of y, when the variables don't match, we end up with dy dx. By the way, if there's only two variables in the problem and it's very clear what dy dx means, you are welcome to write y prime instead of dy dx. A lot of students will do that. I prefer dy dx just so you can see the two variables that you're looking at the ratio between. However, it doesn't have to be that way. So d dx of x squared, I like to think of it this way. The 2 is going to come down. X stays the same to the first power. What did we do there? We did the derivative of the square. We completely ignored the x. We left it where it was. So now we have to do the derivative of x by the chain rule. And d dx of x, the derivative of x, we saw that before, is 1. Of course, I would hope that you would know that the derivative of x squared is just 2x. But 2 times x to the first times 1 is 2x. Why did we do it that way? Well, it makes d dx of y squared much easier. We'll do the same thing. We'll tackle the square first, and that's done exactly the same. It's 2. We keep whatever was on the inside the same to the first power. What was on the inside? Oh yeah, a y. The chain rule is still in effect, so we need to multiply by the derivative of y. And the derivative of y, well, we saw that before when you're going with respect to x, is dy dx. So we would write this as 2 times y times dy dx, or if you wanted 2 times y prime. Make sure your prime isn't confused by a first power, or confused with a first power. Okay. Now, again, this is split between two topics, implicit and related rates. We're going to mostly do implicit differentiation first, though there are a couple related rates that are snuck into here. I feel like implicit differentiation was not very common over the last 10 years, but then it's had a resurgence maybe the last 2 years. It was very common in the mid-2000s, though. So mid-2000s, it wasn't uncommon to see a full free response all about implicit, and they might sneak a related rates in, and then nothing for about 10 years. Then the last couple of years, we've seen usually the last or the second to last free response, no calculator active on these, with implicit differentiation. All right, so let's get started. It's a very common first question. So consider the curve given by this implicitly defined function. This is implicitly defined because an explicit function is typically written as y as some function of x, which means y is isolated on one side and stuff is happening to x on the other. But this clearly has a y on the same side as x, and y is not isolated at all. So we say that the function given is implicitly defined. This first question, very common, show that the derivative of this function is that. All right. Well, to get dy dx, we might want to focus on this y right here. We would have to do d dx of y. So the key giveaway here is this part that tells us what we need to do to the original equation to match the answer. So let's begin. We're going to do, and I'll try to work maybe just to the right. I think I'll have enough room. Again, on an actual free response, it always takes up 2 full pages of paper. So A and B would take up 1 full page, and C and D would take up the other. So you'll have plenty of room. If you run out of room for some reason, you can actually tack on extra paper, but I don't think I've ever had a student run out of room. So d dx of one side and d dx of the other side. And we're doing it of the equation y squared and 2 plus x times y. Now, one thing we don't want to do is do a run-on equals sign. It's very important to realize there are 2 sides to this equation, so we're going to keep those 2 sides. So I'm just going to do an arrow so I can see what's going on, and we're going to work with the left side first. d dx of y squared, we did that up above, no reason to show the extra work. It's 2 times y times dy dx equals, then the right side, the derivative of 2 is 0, X times y, ooh, that looks to me like a product rule. So the derivative of x with respect to x is 1, keep y the same. Product rule has a plus, keep x the same, and then the derivative of y with respect to x is dy dx. Looking pretty good so far, and I was definitely wrong. I'm certainly going to run out of room, so I'm going to cheat and move off to the right. I see 3 terms here. I see a first term, second term, third term. Our end goal is to show this, which means somehow they isolated dy dx on the left side. So I suggest we take the 2 terms with dy dx and move them all to the left side. One of them is already on the left side, so let's subtract this one on the right. And so I think that's going to give us 2y dy dx, the one that was already there, minus x times dy dx equals, and on the right side, 1 times y is just y. Well, in order to isolate dy dx, we only need one instance of it. The nice part is each of these 2 terms have dy dx in common, and the trick for this is to factor. We're going to factor out the dy dx from each of these to the front. That leaves me with a 2y in the first term and a minus x in the second, equals y. And then the last step, hopefully is not too terrible, divide off everything that's not dy dx to get y divided by 2y minus x. Great. If you had solved this and the dy dx had moved to the right and this had moved to the left, you probably would have seen something like this. And I'm not quite sure exactly how it would have worked. My guess, though, is it would have looked like this. Can we see that these 2 are equal to each other? If you're not sure and you're like, that's so close, but the negatives are just weird, then maybe try multiplying by -1 over -1. If you do that, we get a positive y on top, and if you distribute, you get what's over there. You can always multiply a fraction by anything, as long as it's the same on top and bottom, right? So that's a clever trick right there. If you end up solving, or you get something, you're like, it's so close, but the negatives are weird, multiply top and bottom by a negative, and if it matches, then you're golden. All right, usually after implicits, they're going to give you the derivative, which is so important because the next few problems are going to work with the derivative. So let's look at B and C. B asks us to find all the points on the curve where the line tangent to the curve has a slope, and C, show that there are no points on the curve where the line tangent to the curve is horizontal. A lot of students look at these and they focus in on the wrong part. They focus in, they say, ooh, I need to write a tangent line. And that's not what they're asking you here. They're saying, and I'll do the curve in yellow, and I'm going to erase this, but they're saying if you had the curve and it did some sort of squiggle, they're asking you, where are the points x comma y? So let's say this is an x and this is a y over here, where if you were to graph a tangent line, so let's say that this is my tangent line going across. That was possibly the worst tangent line I've ever done in my life. There we go. If we have a tangent line that has a slope of 1/2. So they don't actually want the line's equation. They're saying, we want you to find all the spots on the yellow curve that has a slope of 1/2, because we know that the slope of a tangent is the same as the slope of the curve at its point of tangency. So instead of thinking about the line tangent, what they're really saying is, if we look at this original yellow equation, where does this yellow equation have slopes of 1/2? Well, to find slopes, this is a calculus class, so we're either doing a derivative or an integral. We're going to work with the derivative, of course, and they already gave us the derivative. That's so kind. And they're saying, what are the points x comma y where the answer, or the derivative, right, same thing as slope in this case, is 1/2. So all we need to do is take the dy dx, replace it with 1/2. Now, we need to find the points x comma y, so I suggest you try to isolate a variable here. It doesn't matter which one. I'm going to cross multiply quickly. That's going to give me 2y, and then if we do 1 times that equals 2y minus x. Isolating maybe x would be pretty easy. I'm going to add x to the left side and subtract 2y to the right side. Subtracting 2y from itself gets us 0. What does this tell us? Well, it means that the answer is going to be 0 comma something. and it might be 0 comma more than one thing, because notice if x is 0 up here, whatever y is, if y is 6, if y is 7, if y is 8, they're always going to cancel and give us 1/2. So 0 in our derivative always gives an answer of 1/2, which is great, but that doesn't mean that 0 comma every number, right, 0, 1, 0, 2, 0, 3, and 0, 3.1, that doesn't mean that all of those are on the original curve. I mean, again, if you picture that original curve up here, 0, 1 maybe is here, but then 0, 2, 3, 4, this is every point along the y-axis. And they want to know all the points on the curve. So it is possible that the curve maybe does this, right? So there could be 3 points, 0 comma something. But to guarantee that a point is on the curve, and just knowing the x, let's use the equation for the curve. Y squared equals 2 plus, we know x is 0, times y. Well, that just gives us y squared equals 2. We introduce a square root, so we do need that plus minus here. And so actually, I see 2 points for our answer. 0 comma square root of 2 and 0 comma negative square root of 2. Could you put both of these together in 0 comma plus minus root 2? Sure. But you don't have to. Okay, so there we go. That's that. Part C. Show that there are no points where the line tangent is horizontal. Well, what does a horizontal tangent mean? It means that the slope is 0. So let's do the exact same process. Slope is 0. Treat this as 0 over 1, not 0 over 0. 0 over 0 is undefined. 0 over 1 is the number 0. When you cross multiply, you get 0 equals 1y, so it means y equals 0. All right, so for in order for there to be a tangent line that is horizontal, y must be 0. Are there any points on the curve where y is 0? Let's do the same thing as before. Y squared equals, 0 squared, y is 0 in this case, equals 2 plus x times 0. Well, those are gone. 0 equals 2. Uh-oh, 0 is not equal to 2. And so this shows that there are no points where the curve is horizontal. So I'd say, therefore, y cannot be 0 on the curve. Or maybe even better, I should say there's no tangent line up there, but I've already written it, so the end, there are no points. All right, part D. Let x and y be functions of time t. At t equals 5, the value of y is 3 and dy dt is 6. Find the value of dx dt at time t equals 5. Okay, let's see what we want to find. We want dx dt. And I notice this is a ddt here. That is a variable that's not even in the problem. This is actually a related rate question, just somewhat disguised. So it's probably good to remind you of the structure for related rates. That's actually on my 3rd page here. Related rates are always going to give you a rate that you know. They're also going to ask you about a rate that you want, a rate you're trying to find. Your first goal is to write an equation that relates the variables in the know and the want. No calculus for the equation, just relate them together. Then take a derivative, usually ddt, because related rates often have to do with how rates change over time, quantities change over time, and then last but not least, plug everything in. So let's get to it. What do we know here? That's not it. Second try. What do we know here? And when I say what do we know, I mean what rate do we know? What derivative do we know? Looks like we know dy dt equals 6. All right, pretty good so far. What rate do we want to find? We want to find dx dt when t equals 5. All right. Do we have an equation that relates the variables y and x together? No t's here, just y and x. Well, yes, we do. It's our curve. Y squared equals 2 plus x times y relates those together. All right. Do we have a way to find the derivative? Certainly. Of course, the question becomes dd what of our equation, but that's given to us in the variable at the bottom, we need to go through and do d dt of each side. Now the nice part is you did something very, very similar to this on part A, but our actual derivative is going to be a little bit different. So 2 comes down, y stays the same to the first, times the derivative of y with respect to t is dy dt. And this is one of those problems where you probably don't want to write y prime here and y prime up here, because then you're telling them y prime stands for dy dx, and then you mean, oh, no, 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 down here y prime stands for dy dt. So just be careful or be aware of that. As we move to the right, 0, and then this is our product rule again, so I'm just leaving a little bit of space for it. Derivative of x is no longer 1 because it's d dt, so this is dx dt times y plus x times dy dt. And then we're pretty much set. The last step is the evaluate step, and that's where we substitute in all of our values. So we should be able to substitute in everything except for dx dt, so let's see what we can do. We have 2, then it's going to be a blank. Dx dt is what we're trying to find. Here's y, x, and dy dt. All right, let's go through. What is y? Let's see. Time t equals 5. The value of y is 3, and dy dt is 6. Excellent. Y is 3, dy dt is 6. Uh-oh, we need x. Now, one of the most common mistakes I see students make here is they say, oh, t equals 5. They said t, but I bet they really mean x. Well, they don't. They mean t. And so we're not actually using t in this problem, which is kind of weird. They want x. How do we find x? Well, we know y. And if we know y, shouldn't we be able to find x using our original equation? Let's use a little space down here. We know that y is 3 in this case. So I think we should be able to find x. 9 equals 2 plus 3x. 7 looks like 7/3 will be x. Okay. How do we finish solving? Well, it's actually pretty easy because we're just trying to isolate dx dt. So I'll keep dx dt over here just so you can kind of see the whole process. This is 2 times 3 times 6. I need to subtract this 7/3 of 6, which is a nice number, but I'm not going to worry about it. And then I need to divide the 3 off of dx dt, and I'm done. Remember, we're not simplifying on free responses. We want to go through and make sure we have the right answer. Don't spend extra time simplifying. It might come out nice, it might not. It has no indication on if you did the problem right or not. Stop as soon as you get a numerical answer. All right, second one. You guys kind of have the hang of this. Why don't you see what you can do with it and then come back together. We'll talk about this one, related rates on the third, and give you some extra practice, and that's it for today. Ready, steady, go. So you'll notice this is 2015. It's much more recent than the one on the previous page. Let's see how things have changed. Write an equation for the line tangent at -1, 1. Okay, well, t of x. We need to find the value of the derivative here, which they've called dy dx. So we need to find dy dx at the point -1, 1. I included both x and y because the derivative uses both x and y, times x plus 1 plus 1. All right, just a little side note over here, dy dx at -1, 1 equals 1, 3 times 1 squared minus -1. I should probably work below so I don't run out of room. So it looks like 3 plus 1, I'm getting 1/4. And so my final tangent line here is going to be 1/4 x plus 1 plus 1. The end. Find all the coordinates of the points on the curve at which the line tangent to the curve at that point is vertical. Again, they're not asking you to write a tangent line. You did that up above. They want to know vertical tangent lines. So we have a function that bounces off this vertical tangent. Vertical tangent means what about our derivative or our slope? Vertical lines, which you learn early on in math, have no slope or an undefined slope. That's not a zero slope, it's undefined. So if this is the formula to find our slope, what will make a fraction undefined? That is if the denominator is 0. So we need to find when dy dx does not exist. And to do that, we set the denominator, 3y squared minus x equals 0. I suggest that we go through and determine or at least isolate a single variable, and x I think is pretty easy to isolate here. So whenever the x coordinate is equal to the y coordinate squared times 3, then you will have a place that causes, or a point that causes the derivative to become undefined. I can actually find many points where that happens. When x is 0 and y is 0, that happens, right? If you substitute in 0 and 0, you get something that's true. When y is, it's very easy to start with y. When y is 1 and x is 3, you get a true statement. When y is 2, that's 12, and so on and so forth. There are an infinite number of combinations that will make that true, but not all of these are on the original curve. So how do we determine which one is on the original curve? Well, let's start with the original curve. So the original curve's equation is y cubed minus x times y equals 2. And actually, we just have a system of equations here. Two equations, if you will. You don't need to write it like this, but I find sometimes students enjoy seeing it written like so. How do we solve a system of equations? Well, one of the best ways, my favorite ways, is to use substitution. I'm going to substitute this in for the x in the first equation. So we get y cubed minus 3y squared times y equals 2. And now we have a single equation with only one variable. There's one of these y cubes minus 3 of these y cubes equals 2. This is negative 2y cubed equals 2. Y cubed equals negative 1. Cube rooting both sides. A cube root only produces one answer, negative 1. And so we know the y is negative 1. So for my final answer, y is negative 1. But how do we find x? Well, we take the y and we substitute it back in here. When you substitute that in, hopefully we can see that x is 3. And we're done. Part C. Evaluate the second derivative at the point on the curve where x is negative 1 and y is 1. All right, second derivative, so we need to do d dx of the first derivative. Okay, well, d dx of dy dx, different color, right? We have the first derivative, they want the second, so we're doing d dx of the first derivative equals d dx of y over 3y squared minus x, something like that. Let's make sure I didn't have a copy error here. I copied everything correctly. Great. So d dx of dy dx, that's easy. d is d squared. This is dx squared, nothing bad at all. The right side, though, I see one function divided by another. This has got to be the quotient rule. So to set up our quotient rule is not the product rule. It has a minus. Other than that, it's very, very similar. Like so. Now all we have to do is just fill in the derivatives or keep the functions the same depending on where they are. So we'll see how I do with my spacing. My guess is not too well. We do the derivative of the top, or the derivative of the first. So that's dy dx. Keep the second or the denominator the same. Keep the top the same. Derivative of the denominator, this is the tricky one. I'm going to run out of room here, I can already tell. 3y squared. Might even help you to see it with the extra parentheses. So 3 times 2 is going to give us 6. Y is going to stay the same to the first power, but now I've only done the derivative of the square. We haven't touched the y yet, so chain rule, dy dx. Derivative of x is easy, minus 1. Okay, we're looking all right so far. I think now we have to evaluate this where x is negative 1 and y is positive 1. Let's see if we've gotten any help earlier on. Oh look, negative 1 and positive 1. Didn't we evaluate the derivative at that and find that that was 1/4? Well, when we go through and we do d squared y over dx squared evaluated at negative 1 comma 1, look how fast the answer is going to be. The first part is the derivative evaluated there, which we just saw was 1/4. And then the rest of this, 3 times 1 squared minus negative 1. I'm not taking any chances here. I'm just writing everything that's here. So 6 times, let's see, y was 1, dy dx was 1/4 minus 1. Watch those parentheses. All divided by 3 times 1 squared minus negative 1 squared. The end. I'm done. We're not going any further. right? Simplifying this is a waste of your time, and if you make a mistake, you'll have lost the point. This problem was probably 3 points would be my guess. I bet you'd get 2 points for the correct derivative, and then a 3rd point for the piece here, for the answer. Okay, let's move on to our last set of free responses. These are full related rates. We already discussed the format, so that's not too terrible. Let's look at 2 problems here. Ship A is traveling due west. If you have a picture, it's always a good idea to indicate direction. So ship A is traveling west towards Lighthouse Rock, so we're going this way. And then we'll switch colors. It looks like ship B is traveling north, away from Lighthouse Rock. Okay, let x be the distance, blah, blah, blah. Y is the distance there. It's already labeled. Very nice of them. Here we go. A and B. Find the distance in kilometers between ship A and ship B when x is 4 and y is 3. Then find the rate of change of the distance between the 2 ships. So let's do the first part first. Find the distance in kilometers. This one actually has no calculus, but it's going to set something else up for us. Let's name the distance between them. I think r is probably going to be a pretty common, or c if you think the Pythagorean theorem there. We can see that right angle, yeah. So I'm going to use r to indicate the distance between the 2 ships. We need an equation, and we know, or hope we know, that x squared plus y squared is equal to r squared, right? If you're doing distances of a triangle, a right triangle, Pythagorean theorem is your friend. And in this case, we have 4 squared plus 3 squared equals the radius squared. 16 and 9, I think, is 25. And maybe you recognize that as a Pythagorean triple. So the distance between the 2 ships is 5 kilometers. Lovely. Now what? Find the rate of change in kilometers per hour of the distance of ships, or distance between the ships. Now, kilometers per hour. This is where things get a little bit tricky. So this is related rates, rate of change. So let's start with what we know and then what we want. The know. What rates do we know here? Well, we know ship A is traveling at a rate of 15 kilometers per hour. Okay, and how do we write that? Well, this is ship A, but ship A is this x right here. So the distance x is changing dx dt at a rate of 15 kilometers per hour. 2 things to note. X is in kilometers, time is in hours. Those need to match up. And also, I've made a mistake here because we need to realize that this distance x is decreasing. And how do you show a decreasing rate? With a negative. We know this is decreasing because the ship is traveling towards Lighthouse Rock. Hopefully it turns at some point. Do we know anything else? Yeah, I think we also know dy dt. And we know dy dt is moving north, so that's increasing, so it says positive 10 kilometers per hour. Great. What rate do we want? Well, we want the rate of change of the distance between the 2 ships. I called the distance between the 2 ships r, so we want dr dt when x equals 4, y equals 3. And I always put these with the want because we need to know that those aren't constants. Depending on where the ships are, those x and y values are going to change, which means when we get to this next step, when I get to my equation, I do not want to use these in my equation. I want an equation that has x, y, and r. I'm not going to replace the equation's x and y values with those over there. What equation uses x, y, and r? Oh yeah, this guy. We've already done it once. So x squared plus y squared equals r squared. Lovely. Well, then I think we need our derivative. The derivative we can see as d dt. We saw that time is in the denominator. That's the indication of how we're going to take the derivative. d dt of each side. Okay. As we go through, derivative of x squared, 2 comes down, x stays the same to the first, so that took care of the square, but I haven't done the derivative of x yet, so we need a dx dt. The y is similar, 2y to the first times dy dt, and then the other side, 2r dr dt. Okay. Last but not least, we need the evaluate step. Before we evaluate, I'm going to simplify this or at least rewrite it. Notice you can divide out a 2 all the way through. So really it's x times dx dt plus y times dy dt equals r times dr dt. All right, let's start evaluating. We know in this case, and actually let's leave all the blanks, so blank, blank, what are we trying to find here? We want dr dt, okay. Blank, blank, blank times dr dt. There we go. All right, well now we can start evaluating. We know x is 4. We know dx dt is negative 15. We know that y is, where is y over here? Y is 3, and this is 10. And we found r earlier as well. R is 5 over here. Very nice. Okay, let's finish this off. No math here. This is probably a no calculator active problem, so my final answer, 4 times negative 15 plus 3 times 10, all divided by 5, equals dr dt. I should have left a gap. It's always good to indicate units. General rule of thumb is if there are units in the problem, then you should probably put units in the answer. Now, they won't dock you here because they would say indicate units in your answer, but I'm going to put them anyways. R is in units of kilometers, and T is in units of hours. And we're done. Last one. Let theta be the angle shown in the figure. Find the rate of change of theta in radians per hour when x is 4 and y is 3. Oof. Okay, so we have theta up here, and we should probably start filling in our no's and wants and all that. The no is going to be the same up here. We know all of this, so I'm not going to rewrite that. I am, however, going to write the want. We want the rate of change of theta in radians per hour. So we want d theta dt. All right, so then we need an equation, and this equation somehow has to relate x, y, and theta all together. All right, well, how do we relate all of those together? Well, whenever you relate theta to something, I believe that's going to bring trig into this. Now, there are a few ways to do this, and I'm actually going to list all the ways, and then I'm going to erase it after that. So, we could say that the sine of theta, and you might want to pause and just watch me write this first. The sine of theta is the opposite over the hypotenuse, right? So the opposite in this case is y, the hypotenuse is r. So sine of theta equals y over r. Of course, you could do cosine of theta, which will be x over r. You could do tangent of theta, which is going to be y over x. Now, all of these are fine, and they will all get you the right answer. But because eventually you're going to be doing a derivative, then you get to pick which one of these you want to take the derivative of. And I'm probably not going to do the derivative of 2 of them. In particular, I'm not going to do the derivative of tangent because that's secant squared, and I don't want to deal with secant squared. And I'm not going to take the derivative of cosine because that gets me a negative and no reason to have an extra negative. So I'm going to pick the sine. You could have used any of them. Now, we want d theta dt, so I need to take d dt of each side of this equation. So we have this y divided by r and this sine of theta. All right, d dt of sine of theta, well, that becomes cosine of theta, but that's only the derivative of sine. I haven't done the derivative of theta yet. The derivative of theta is d theta dt. You don't want to forget that because then d theta dt won't be in your answer and you'll be very confused. On the right side, I see 2 functions dividing by each other, a quotient, which probably means the quotient rule. Don't think that you can replace y and r with, let's see, y is 3 and r is 5. You can't do that because we want this derivative to work for any value, right? It needs to work for this relationship for any y and any r. If you replace them with constants, then the whole thing just becomes 0, and that's not useful. Okay, so here's our derivative. We get dy dt, keep r the same, minus, keep y the same, dr dt, all divided by r squared. All right, let's do that evaluation piece. Okay, so evaluation-wise, the first one's kind of weird, cosine of theta. Well, cosine of theta, trig functions are always represent a ratio of sides. So cosine of theta up here is going to show us the ratio of x to r. And now that we're actually evaluating, we can replace x with 4 and r with 5 now that we're substituting values in. So x is 4, r is 5. So cosine of theta is going to give us 4/5. We don't even need to know what theta is because we can see the sides of whatever theta is for our triangle. So 4/5 times, oops, I'm not sure why I'm going over here. Second try. 4/5 times, we're going to leave d theta dt because that's what we're trying to evaluate, and then start filling in the rest. dy dt I think was 10 if I remember. There it is up above. So we get 10 times r was 5 minus y was 3, and dr dt, oh, I think we found dr dt. Oh, this is a bummer. This is way up here. It still works. You could do some quick reducing if you'd like. It's useful that we found dr dt, or you could be really lazy and just rewrite all of this. But just in the interest of space, what do we have? Negative 60 plus 30 over 5. So that's negative 30 over 5. I'm looking at negative 6. There we go. Okay, so r is negative 6. Great. I think the last thing, oh, we need to divide by r squared. There we go. It's a 5. Last but not least, we need to get rid of the 4/5. Don't divide it. Don't do anything weird. Just d theta dt equals, and you can do a little simplifying if you're feeling confident, times the reciprocal. To get rid of 4/5, you multiply by 5/4, and you're done. All right, if you wanted units, theta is in radians, and time is in hours. Ta-da! Alrighty, now related rates probably will show up one time on your free response somewhere. It's very unusual to see a full free response that's all related rates, especially these days. It'll probably show up where you just have to do ddt of both sides, or maybe it'll be implicit or something subtle. However, it will certainly show up in the multiple choice. And I find a lot of my students really want more related rates practice because they get scared of it. And related rates can be challenging. I mean, there's 5 steps every time. And really breaking down what's given in the problem can be tough. So what I've done is I put together a couple pages of multiple choice practice, 11 multiple choice problems. I've given you the answers here so that you can work through and make sure you get those answers. But if you get stuck, I do have all my worked out solutions posted on Teams as well. So you have all this practice. You want to be confident on related rates, even though it's not going to be a huge portion of the exam. Expect at least one multiple choice and at least one free response part of the exam on here, and be confident on it. They're not too bad. Once you get that want, no equation derivative evaluation, you'll be doing just fine. So thank you for tuning in with me, and hopefully you're feeling more and more confident every day for that AP exam.